Hello everyone, welcome to today's webinar. I can tell you it is hot and sunny in the south of England this afternoon, which on the plus side, I probably have better lighting today and maybe you can see me more clearly, but on the negative side, maybe you can see me sweating as well. Today's topic is thinking in APL. Array-oriented solutions. And these are two phrases that come up a lot when you read about especially learning and teaching APL and the sort of language design stuff, philosophy of language stuff. Certainly the thinking in APL stuff maybe involves a bit more philosophizing and pontificating, and a certain group of APLers and people are interested in that. But hopefully I'll be able to provide something for the more pragmatically minded people who just want some hints and tips on how to get stuff done and how to improve their problem solving. So when we talk about thinking in APL, here's some of the things that sort of can be brought up. There's obviously tool of thought, which I'll mention more in a moment. There's stuff about language and cognition and the way that your thinking is linked with the language that you use. There's obviously knowledge of the primitives from APL and other array languages that are derived from APL, and even like the idioms, which I guess for us are more or less like set phrases, although you can also adjust them for your needs. Array-oriented solutions, on the other hand, is a bit more general, can apply to people who aren't necessarily APLers specifically, but they might have heard of, you may have heard of array-oriented programming. You either want to find out what that's about, or, you've found out a bit about what it's about, but you just want to know, okay, what is it exactly and how can it help me and how can I use it to aid in my own problem solving, no matter what language I'm using. And this includes things like considering the array as your unit of sort of data, your unit of thought that you're working with, in a sense. APLers like to talk about direct expression, often in contrast to abstraction. Our array-oriented solutions, do they involve using a specific set of techniques? Do I need to read a book and learn a bunch of specific techniques to do array programming? And something else called heuristics, which I'll get to more later. So that's the kind of, overview introducing what this topic is about. It's quite broad, which again is why we're going to be doing a sort of multi-part series here, talking about different aspects. For today's webinar, it's going to be largely food for thought. I know that lots of people in the APL community are interested in this type of stuff because I've read some of your papers about it. And this is a live webinar, so if you're watching on dialog.tv, there is a live chat there. My colleague Adam is sort of monitoring that, and he'll be able to forward me any of your comments or questions as we go through this. And then, again, talking about the more pragmatically minded people, people who just want some hints and tips to get stuff done, there'll be a little bit of the secret sauce, some techniques, very much beginner techniques or stuff that you learn early on in APL for today, but kind of showing you the type of thing that can help you become a better array-oriented problem solver in general, and also improve your APL skills specifically. So I'd be remiss if I started this, addressing this topic without mentioning Iverson's Turing Award paper, Notation as a Tool of Thought. He sets out these sort of guidelines or indicators for what makes a good notation. I'm not going to go into all of this. If you want to see someone knowledgeable talking about this stuff, there's this functional conf talk by Aaron Su. He goes over these in a bit more detail. If we expand our topic from notation as a tool of thought to language as a tool of thought, then we can get some broader things, which will obviously apply to the notation, but might also be interesting to think about just in more general terms of problem solving, even if it's outside of a specific notation. And this is things like expression. We want to express ideas using language. Suggestivity. This is the concept of, some construct, some phrase or construct you have being applicable in more than one place or in places other than the context in which you originally devised it. So, in terms of natural language, I like to think, people like similes, people like metaphors, saying this is kind of one, right? If we can relate our ideas to more familiar things, that's also useful. It helps to engender an intuition, right? Being able to do things without having to painfully think about them all the time. Subordination of detail. And this is in contrast to plain abstraction, as in giving a name to something so you don't have to look at the guts anymore. Subordination of detail includes things like the sort of functional forms, things like reduction. We're abstracting away the innards of what the computer's doing, but we can still have access to the level of detail we need in order to have malleable expressions. We can get more power from the suggestivity if we're able to manipulate some of the details. And then economy, which subordination of detail kind of leads to economy, especially in the case of our notation. And APL is, famously terse. So another note on economy really and its benefit comes from this conversation between Brian Cantrell and Arthur Whitney. I don't know where this number comes from, and as we get more towards the kind of philosophy of language, language and neuroscience, language and thought, start to get into a realm of things which A, I'm far from an expert in, and B, I don't know if there's loads of concrete evidence for some of the things that get said about this. But, for example, the idea that we can keep 7 thoughts, 7 things in our head at a time, and so having this notation that's really economical, terse, and subordinates detail in this really useful way means that we can have whole, your line of APL should probably have up to 7 things. And then this other anecdote about if you're Cantonese, it's 10, and Roger Hui preferring to do maths in Cantonese because it's faster and more regular, which I think is really interesting. But I obviously hesitate to use this as like solid evidence that APL is somehow better than other languages, even if that turns out to be true. So that's kind of framing the conversation. Let's try and get a bit more specific now and ask, what is APL thinking? Obviously, we can rephrase this. It's the thought process of someone using APL, but that doesn't tell us much more. So we can ask some questions to try and narrow that down. Is APL thinking just, the vocabulary and grammar that you use? Is it knowing the primitive functions and operators and what they do, and therefore being able to construct your expressions, being able to express your thoughts this way? Slightly more useful than this is a thought about, is APL thinking the act of translating natural language algorithm descriptions? So, I believe a lot of people approach problem solving like this, and you certainly learn it when you learn programming is, you have maybe a problem description or even a sort of overview of a solution. You then break this down into a set of discrete steps, which we often call an algorithm, and really the rest of your task is digging into each of those steps until you find something in your language that makes you go, I know of a thing, I know of a construct in the language I'm using that does that. So I know we can go from there and build up the details. Often it's said that APL is much closer to the problem description. And so once you've broken down your solution into this sort of series of steps, this algorithm potentially written as pseudocode, then oftentimes you can get like a one-to-one translation with APL between a line describing one of your steps and a line of APL. Is that APL thinking? Something much less interesting is translating code from other programming languages into APL. We know that word-for-word translations are notoriously inefficient, not very good, certainly not considered array-oriented most of the time. But obviously looking at the comparing and contrasting programming languages is obviously interesting and often useful. Then there's even more trivial, the translating mathematical formulae. I mean, since APL is a mathematical notation, I mean, it's pretty trivial in most programming languages. Maybe it looks nicer in APL. It's a matter of opinion. To what degree is APL thinking knowing and using specific APL techniques or specific array-oriented techniques? And again, I mentioned this problem-solving heuristics, which are kind of approaches to problem-solving when you're not sure how to go. So lots of interesting stuff. Honestly, could talk for a very, very long time about all of this. But for today, we're just going to look at some specific techniques and these problem-solving heuristics because they're a bit more practical. We're only going to look a little bit. Yes, so for the pragmatic viewer, someone who just, has learned what array-oriented programming is, wants to get as much out of it in as little time as possible, what are the techniques and what are the approaches I can take to do array-oriented problem solving? Perhaps more importantly, how do I know when I'm going in an array-oriented direction? Or the slightly easier one is asking, when do I know I'm not doing something array-oriented? And this often boils down to this idea of treating the array as a unit rather than the individual elements in the array, sort of doing things, applying your functions on these array units. So we can look at an example, a super trivial one, but I think it gets the point across. I don't personally remember when I learned to count, but I know the stereotype of children counting on their fingers, and it's basically following this algorithm described here. So I have my array, which is my hand. For each finger element in my array, I'm going to increment my internal counter. So 1, 2, 3, 4, 5 fingers. Another reason I like this example is I've read in some of the papers that I'm referencing today, people talk about how it's not actually, like in favor of APL, they say it's not natural to think in a kind of scalar looping way like this, right? But this is definitely how children count, right? So I'm not 100% convinced by that argument. If you want to look at an array-oriented approach, I mean, to what extent is APL thinking, knowing and using the symbols? If you're asking that, then someone could argue, well, this is more APL-ish because, there's no keywords, everything's symbolic. It's a similar thing. It's not exactly the same as the for loop from just now, but it's very similar. It's also, not a very great approach. This is counting elements of a simple vector, by the way. Didn't quite clarify that. Recently, when teaching APL a couple of times, say recently, half a year ago now, we've used this example. It's almost like one of the broken keyboard problems. How do you count the number of elements in a simple vector if you don't have tally and you don't have the shape function? And this is one that we'd like people to arrive at, where it is really, even though it's not the primitives, it's still an array-oriented approach, because you're using one of these. I mean, this is an example of a specific APL or a specific array programming technique, a scalar primitive, which maps implicitly between all elements in omega, and a reduction. Right, it's a very common technique. If you're interested in economy, you can also talk about how, we can get rid of the references to omega and have this, derived function. And people who learn tacit programming, trains, and derived functions often get an extra level of the power of economy, where you start to recognize common idioms and phrases in tacit notation for what they are, the functions that they do. So you find that after a while, you're not having to go letter by letter, symbol by symbol, and decode these, but you can recognize them all as one unit themselves. So not just array as a unit thinking about it, but also your sort of function unit chunks that you can compose together, especially if you start to approach APL using a functional style. Having said all that, obviously, in terms of performance and everything, you're aiming for primitives. Nothing really beats the primitives. Another quick example, won't spend too long on it. The logic here is in the innermost loop. That's how we know it's not really array-oriented. In fact, I've cheated a bit here by using membership. Adam pointed out to me that if this was truly scalar, it should be if letter equals A, else if letter equals E, else if letter blah blah blah. But I've saved us all that pain. This is the array-oriented technique to get the same sort of thing. This is, again, scalar primitive function, and this time it's a compression. So we'll look at some more stuff similar to this. So yeah, for most of the sources coming up, actually I think I'm just using the first one. Brian Becker actually pointed me in the direction of this paper, Robert Metzger's APL Thinking, Finding Array-Oriented Solutions, hence the title of the webinar, and said there's probably some webinar content in there, and I've gone and got carried away and read too much stuff and have too much to talk about. There'll be more sources at the end. So if we want to look at to what degree are array-oriented solutions, to what degree is array-oriented problem solving knowing and using primitives, what all the primitives do? Do you need to learn what every primitive does before you even start approaching array-oriented solving? No. Do you need to know a bunch of idioms to do specific things, or just being aware that they exist is obviously useful? What about specific techniques? We've just seen a couple, and we're about to get to this mysterious word heuristics. Don't you worry. Primitives are in the language bar if you need to know what they all do, and that's just a thing you develop over time. It's just gradual exposure to more and more of them, and eventually you find yourself piecing things together in ways that you didn't think you could before. In terms of idioms, it's never been easier for the APLer to find and use code snippets of people who've solved the same problem as you in the past. Next week, Adam will be talking about applecart.info, which is about to turn a year old, the domain. I think the project's a bit older. So to find out about that, search for BAA Webinar Schedule 2020. It'll be on one of their Zoom meetings again, as we continue to interleave Dyalog webinars and BAA webinars. Just make sure you go to the right the right BAA, because apparently the astronomers are doing weekly webinars as well on Zoom. The website looks like this for us. Sorry, it's just hot. So yeah, primitives, and there's idioms. There's some specific techniques, which I've separated from idioms because idioms are made out of these, but so are all your other solutions. And, you'll generally be modifying these things to suit your needs. So we've just seen a reduction and scalar. A reduction applied to the result of a scalar dyadic primitive, and then comparison function usually, and a compression. That's some examples of specific APL techniques. So finally to this mysterious word heuristics. So in the paper which has inspired this webinar, Robert Metzger talks about heuristics in contrast to algorithms. So whereas an algorithm is like a specific set of steps, follow these steps and you'll arrive at this result, definitely, unless there's some random number generation in there or some floating point error. Anyway, it's like a recipe, right? Here are some explicit instructions, do these and you'll get exactly what you want. In contrast to that, a heuristic, he says, is more like a sort of trick, an approach, a guideline to trying to solve a problem, especially if you're not sure, you're stuck, you don't know where to begin, or you don't know where to go from where you are. He lists these 7 heuristics and talks about them in decreasingly specific detail as you read the paper. And for right now, we're just going to look at a couple of examples of the value first and the shape first approaches, which I think any APLer will probably recognize it as something that they've done, even if they haven't tried to name the process and think about it in this way. Yeah, they're 2 pretty basic approaches to solving problems in APL. And then in the future, we may address the other ones. Well, probably will. Anyway. So, an example of value first. The idea is the idea is that your array result has values and shape. And more than that, any element in there has a value and a position. So the value first approach is saying, generate a load of values. The ones I want should be in there. I probably am going to end up generating even more that I don't want, and I'll just lop off cut the fat, get rid of the ones I don't want. So our example is the to function. So find me the integers from alpha to omega inclusive. And here's a value first approach. We generate the values using the index generator iota. So it's numbers from 1 to 7, chop off the first 2. Right? You can also do this with compression instead of the structural functions there. Give me all the numbers 1 to 7, only return the ones which are greater than alpha. Hopefully nothing shocking here. In contrast, this is a shape first approach, where we're going to start, we say, okay, we know how many elements, we know the shape of the result we want. It's 3, 4, 5, 6, 7, 5 numbers. Okay, so let's generate an array of indices that has 5 numbers, and then just do some kind of arithmetic or some kind of mathematics to turn those values into the ones that we want. You get an added benefit in this case, since the previous one only works for positive integers, whereas this shape first approach happens to also work if you have negative alpha, which is kind of neat. So sometimes it's worth or sometimes it might be worth taking another look and using another approach to see if you can get something that's more general. If that's of interest to you. Another example, just to sort of solidify this, and then I'll talk a little bit about language stuff again, and then we'll wrap up. So modern APLs with general arrays allow you to have a vector argument to iota, the index generator, where your argument describes the shape, right? So if this was the primitive iota, you'd have all the invalid indices. You'd have a 4 by 2 by 3 array, like 4 plane, 2 row, 3 column cuboid, containing all the valid indices into an array of that shape as some kind of nested array. The problem posed in this paper to demonstrate value first and shape first is we're going to give a vector argument to an index generator, and we want to generate a sequence of these index runs, right? So give me 1, 2, 3, 4, 1, 2, 1, 2, 3. This is, I've converted it into a defin and slightly modernized the way it looks, but this is from that paper. We start by generating the maximum length run, so 1, 2, 3, 4. Then in this case you generate some matrix so that you end up with 3 rows, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So now you have, and if you ravel that, it's a 12 element vector that has all of the values that you want in your result. And the last part is just another filtering process. Yes, I have realized since that if you took another approach to generating n, you wouldn't have to do all these ravels. Don't worry about it. In contrast, let's look at a shape first approach. So in this case, we know that we want, 4 numbers, then 2, then 3. So that's 9 numbers, I think. That's 6, 7, 8, 9. So we can generate a vector of ones of that length. Then we could use, for example, indexed assignment to modify the values in place such that we end up with in this case, an array of mostly ones and a couple of negative numbers, which when you plus scan them gives you the result you want, which is pretty neat. I think, okay, yes, I'll show you this one bit. Is it not dangerous? I'm getting a question now. Is it not dangerous for performance to generate too much data and then filter or chop? And this massively depends on your case, your algorithm, right? In some cases, especially if you have a small search space and you know you're going to always have a small search space, it's almost definitely more efficient to use the primitives, even if your algorithmic complexity is more like, n squared or something, you're generating all this superfluous data. It's almost certainly better for performance than using some kind of control structure like a for loop and if statements, which are going to cause you to have a massive interpretive overhead as the interpreter goes through reading the lines over and over. When you get down to the primitive level, you're accessing the optimized algorithms written in C that the interpreter has. So it does depend on your use case. I remember, for example, from, was it last year or 2 years ago, the problem solving competition I did a webinar and I discussed the Boggle solutions. And they were both sort of quite array oriented, mostly primitive using solutions with different performance considerations in different cases. So I talked about that then. And then Brian Becker messaged me saying, oh, my solution outperforms all of them massively, and it is a looping solution. So I think, and that was to do with searching through a boggleboard, right? So obviously for something two-dimensional, finding, all your values can end up being absolutely massive. So yeah, is it not dangerous? Most of the time, no. Most of the time, when you think in this way, you can access your solution faster, and then you've solved the problem. If later on you find out that you're having problems with performance because of that bit, it's only going to be one or two lines, a couple of lines at most, that's your bottleneck, and then you can take that one specific part and refactor it to be more performant if you have to. Most of the time, you want to be using the primitives where you can. This is just, again, modernizing. Yeah, so instead of, here you have a temporary variable, I, and then we're updating values in place. If you want to take a more functional approach, and again, we can ask this question about to what extent is knowing different primitives useful to aid your problem solving. If I was doing this and I'd discovered this solution, I'd probably go straight for at. I don't know why exactly, but this is the exact same thing basically, but instead of modifying I in place, we essentially merge. It's called merging. I don't know what the technical functional jargon is, but you basically generate a new array that has these new values and then do the plus scan like this. Sometimes saying these values at this condition or at these indices has a bit more of at least to me, a bit more of an intuitive feel than indexed assignment even though indexed assignment's older and more common often. I still do, I'm not opposed to square bracket indexing. So that's, I've been talking for quite a while. There are lots more examples. There's lots more stuff that we can talk about. I'm also interested in hearing what the viewers out there think. I know that lots of people have opinions on this type of stuff. While I wait for questions and before I wrap up, so those was a couple of heuristics and a couple of specific techniques for problem solving. While I wait to see if anyone has any more questions or comments they'd like to ask, or things that you'd like to see explored in this sort of region of APL topic, it's quite broad. While I wait for comments and stuff, I'll ramble a bit more about tool of thought, language stuff. So in the paper where I've got these examples from today, and you see this sentiment expressed a fair amount in APL conference papers, this idea that he puts forward the idea that the computer language you use influences how you understand and solve problems. And I think from a lot of anecdotal evidence, especially APLers, I think believe this quite strongly. But I as well, I get quite excited about this aspect of language, philosophy of language and language design, and as well as the relations, between especially APL and other programming languages and natural language use and acquisition and stuff. I have to watch myself and try to be extra skeptical as you start to wander into the regions of linguistics and things which I'm not an expert in, and the evidence isn't super strong. So this concept of the computer language you use determines how you understand problems gets close to this idea called linguistic determinism, or I think there's some other names for it. where the language you use, even your natural language, heavily influences the way you reason about the world, right? This is something that apparently comes in and out of fashion in language academics, and people find evidence for it, evidence against it. I don't think it's that concrete an idea. One of the most interesting examples I've seen, that I think is fairly well accepted-ish, is from this paper, Can Language Restructure Cognition? The Case for Space. And here they looked at an Aboriginal Australian language, I think some other languages, that either as well as or instead of your relative spatial words like left, right, front, back, they use words that are equivalent to north, south, east and west, often in relation to some physical landmark. And instead of saying something like, from your left hand, they would say from your west hand, or the equivalent. So I think that's quite interesting. And it's the type of stuff that would need to be explored more before you could have any real certainty about going around claiming that one language or the other is better or worse. One paradigm or another of programming is better or worse for solving problems, even though APL is obviously like arrays. If you want to read more about this, look up Sapir-Whorf hypothesis, and there's a Radiolab podcast episode called Words, which I really enjoyed. I think that's the one where they talk about people who were born deaf, and as a result, where they were, they never ended up learning a language for speaking and listening. And so it's quite interesting to hear about how apparently they managed to communicate a kind of long-winded storytelling. Apparently, if they would do a whole 20-minute acting out of bulls and stuff like this, a whole 20 minutes or so just to express what you'd say as, oh, remember when we went to the bullfight last week? Something like this. So I thought that was quite interesting. If, again, I'm kind of using it as cautionary tales against don't get too gung-ho on saying APL is the best for everything because of thoughts, right? Got to be careful to know that you're being right. Here's a lot of the stuff that I read, and we'll continue to pull examples and things from for future webinars. After this is finished and published on YouTube and whatnot, there will be a link in the YouTube description. Yes, I intend to return to the list of heuristics in future episodes. I've just been asked. And more so than that, so I want to get some nice concrete examples of using these heuristics ideally. I like to demonstrate and also to learn through examples, so that would be ideal for me. But also, it's not an exhaustive list of heuristics, and I think there are probably lots of other things, and I'm hoping people will inform me of approaches that they personally use if they have that sort of metacognition and they've thought about this before, like, oh, what am I doing when I try XYZ approach? So I'd like to hear from people what they actually use in real life and what's been successful and what hasn't been. And yes, we can address more heuristics, which I think is probably the most useful part of this if you're all pragmatically minded. So other than that, we've looked a little bit at the world of array-oriented solutions, tried to start to define them in some useful sense, even if it's not a very rigorous sense. And I talked a lot about language stuff. Cool. So, as mentioned earlier, next week, Adam Brzezinski presents Apple Cart. for its 1 year anniversary. Happy birthday, Apple Cart. It really is pretty great, to be honest. It's like all of the idiom lists shoved together and some more. I mean, that's one thing I did think about, and I promise I'll wrap this up now since I've only had a couple of questions, is whether this topic is actually more appropriate to British APL Association webinars, and maybe I should transfer to doing them there for this topic. But I rely quite heavily on Dyalog specific things for my examples. And, similarly, when you think about Apple Cart, I think a lot of the idioms have been dialogized, some of them. Anyway, just something I thought about. And then the next Dyalog webinar will be Adam presenting, again, language features of Dyalog version 18, which has been released now. So you can actually start trying these. Go back to the previous episodes and give everything a go. This will be part 3 now because there's just so many language features in Dyalog version 18. So, yep, that is it. I'm just giving another 30 seconds or so because I know I'm at least 30 seconds delayed from getting any feedback. Otherwise, thank you for listening to me prattle on again. I hope you find this interesting. I hope you found at least some of it useful. And I will be returning to this in future videos. Okay, I'm going to call it there. I'll pop into the chat to see what's going on, but thanks very much for watching. Join Adam next week on the British APL Association Zoom meeting, and join Adam again the week after back on dialog.tv. Thanks very much. Goodbye.